All right, awesome. This is for you, Mr. Krabs. So, nuclear physics and astronomy. So, there are, as you guys probably already know, there are two different types of nuclear processes that you typically talk about in nuclear physics. There's fission and fusion. So, fission, splitting stuff apart; fusion, sticking stuff together. It's pretty simple, right? So, first, I'm just going to give you a brief overview of nuclear fission. So, nuclear fission is one of the two processes that we've actually been able to replicate in a nuclear reactor capable of producing energy. It's actually a fairly simple process compared to nuclear fusion for a couple of reasons, and we're going to get into them in this presentation. But basically, you take a fissile uranium-235 atom, you smash it together with a neutron. The neutron enters the atom and causes it to destabilize. So it creates a uranium-236. There's too many neutrons for the thing to hold itself together anymore. So it splits apart, releases a gamma ray of energy, and launches some byproducts, which can vary. They don't have to be krypton and barium, but they can be, along with other neutrons that are propelled by the energy released by that explosion to hit other atoms and cause a chain reaction. Now, just a little background before we start this. Actually, I just realized you might not recognize the when I write different elements, I'm going to write them in just the nuclear notation of their atomic number and their mass. So 92, when I write U with a 92 and a 235, that means there's 92 protons and 235 total atomic particles. So that's protons plus neutrons. So just so you can follow along. All right. So this is nuclear fission. We managed to produce this in a nuclear reactor in a controlled way in order to produce energy, which is great. However, nuclear fusion we have not been able to create in that way, and I'm going to explain why. Just by explaining the process and by analyzing the sun. So a couple things to know before we start. Just also, if you didn't know, if you've never come across this concept before, the concepts of alpha decay, beta decay, and gamma emission. They look really complicated. There's all these numbers and things. They're actually not that bad. So alpha decay is when you have a parent atom that gets excited by some sort of incoming energy that splits it into a daughter atom and an alpha particle. So an alpha particle is literally helium 4-2. Just a regular helium atom with two protons and two neutrons together. That's what we're talking about when we say an alpha particle. Now remember the concept of an alpha particle. This equals alpha particle. Because this is actually going to be really important to understanding how this pertains to astronomy. So that's not too bad. Beta decay is also not too bad. Basically, with beta decay, is what happens is you have another atom that has too many neutrons in it. So one of the neutrons decays into a proton and an electron due to that nuclear force. So you end up with a process that looks kind of like. There's a lot of different ways of writing this, but it turns into electron and proton. So that just happens as a spontaneous process of nature. That's also kind of important to understand. You'll see why later. So that's not too bad either. There's also just gamma emission, which is where you have an excited nuclear state, which I'm not going to fully get into, but you all you have to understand is that when a parent atom in an excited nuclear state drops to its non-excited nuclear state, it emits a gamma ray, and that's just called gamma emission. It's not too bad. So those three are pretty important for understanding the mechanisms that can happen in stars. Yeah, I think I covered all that. So when we look at nuclear fusion, it seems obvious that you want to smash the smaller particles together to get larger particles, right? So obviously you want to start with hydrogen. So let's fuse some hydrogen together and let's do a little bit of math. So let's say you have a hydrogen 1/1, which is where hydrogen naturally rests, plus another hydrogen 1/1, and they react together to form helium 2/2. Now what's wrong with this? Well, obviously because helium 2/2 doesn't exist, this can't happen. So you can't just have two protons together without any neutrons. You need neutrons neutrons in the atom to make it work. And so you can't just smash these two together. You have to do something different. So the next best option up from this is to use deuterium fused with hydrogen to make a 3/2 helium product, which is stable. It doesn't create energy, but it's stable. And even better than this still is to take tritium, which is a 3/1 hydrogen isotope, and fuse it with another hydrogen and 4/2 helium, which is, if you remember, is an alpha. So the process that happens in stars actually has to create these types of isotopes before it can actually fuse anything at all. So yeah, I'm just briefly going to go over the proton-proton chain that happens in stars. So there's a couple of things that have to happen in a pretty fast sequence in order to create a continuous process of fusion in stars. So first, in a star, you start out, I'm just going to keep track of where our star is over here. Just going to tell the circle. So let's say this is our star. It's a whole bunch of hydrogen, right? That's basically what happens when stars are formed. There's a giant cloud of hydrogen. The thing starts pulling itself together through gravity over time. It falls in faster and faster and faster. And it's actually easier to understand this when you think about the gravitation equation. So force equals G m1 m2 over r squared. Because it's inversely proportional to r squared, as things get closer together, the amount of force between the particles goes up exponentially, and it becomes a runaway process until just the average mass point in the cloud becomes the center of a congenial star as things come together. So the gravity of that star mass eventually becomes hot enough that it can create nuclear fusion. So when it reaches a certain temperature, it gains the ability to overcome the Coulomb force between these particles. So another thing to remember about hydrogen is that it is a proton, and a proton is positively charged. And we know that Coulomb's law says, this is just me relating it to our physics unit this year, so what's going on. The force between two positively charged, or similarly charged particles, Q1 over Q2 over 4 pi epsilon naught r theta. Y'all remember that, right? So in order to fuse two hydrogen nuclei together, you actually have to overcome this force. So remember this is also going to be important as we go. So hydrogen atoms flying around, and because they're hot enough due to the gravity of this giant structure, they come and they smash together and they form this complicated process, which I'm going to briefly try to explain to you. So due to the weak nuclear force, the gravity of the star will cause some of the protons that are just flying around the star to actually change into neutrons. It's this really weird process where you have an up-down quark combination, which is a proton, and one of them gets switched to be up-down-down, which is a neutron, plus some other byproducts, including a positron and a neutrino. So that's what actually the telescopes located underground are meant for. They measure the neutrinos coming off of different stars and different objects in our galaxy in order to try to figure out what's going on. So the neutron sticks around, the positron dies because it's a positron. You can't have a positron in the universe of matter. And the neutrinos fly away and they don't interact with anything. So the neutron is the only part that's really important. So a neutron does not have charge, so it's not going to be affected by this at all. Because if one of these Q values is 0, then there's no Coulomb force trying to keep these particles apart. So all the hydrogen 1 floating around becomes a perfect target for this neutron to latch on and become deuterium. So it becomes 2/1 hydrogen, or helium. Hydrogen, yes, hydrogen. And then as this, when this forms, it has a certain amount of time before it'll just decay back into regular hydrogen to merge with another hydrogen 1/1 to form helium 3/2. Helium 3/2, it is a lot more stable, but it's still not entirely stable. It wants to break back apart into its product. So once that happens, just out of sheer likelihood and the sheer size of the star, the amount of particles that are interacting with each other. You need a 3/2 helium to meet another 3/2 helium. And what you're going to end up with is a familiar looking 4/2 helium plus 2 protons plus energy. And this is important because this reaction right here actually has energy on this side of the equation. All of these things that have happened up until now take energy, and they're taking the energy of this giant star and its gravitational force. So the gravitational force drives these processes until you reach this reaction right here, where the helium 3/2 reacts with itself to produce energy on the other side, and all of a sudden it becomes thermodynamically favorable for it to stay as 4/2 helium or an alpha particle. So once this starts to happen, and there's about a 60% chance of this happening once the atoms start hitting each other. So it's a fairly fast process in comparison to other processes that take place in stars. Yes, Connor.
Is the 60% chance like for the star or for
a particular hydrogen atom? So if a particular hydrogen atom undergoes this first step of becoming a 3/2 helium, there's a 60% chance of it making it all the way to this stable state. And that's just, I'm going to mention percent chances of these certain things happening just to give you a context of why stars live for so long. Because we're going to get to one that's going to be nuts. Like there's like a 4/10,000 chance of it actually happening, but it is the main process of a star. So once you get to 4/2 helium, you're golden, because 4/2 helium will actually stick around. So in our star over here, we because of the gravity of the star, we start forming a core of helium. Now, that helium 4/2, what's different about helium 4/2? Well, there's two protons in it, and that's going to change the amount of Coulomb force that we actually need to smash them into each other. Because if Q1 and Q2 both go up by 2, then the repelling force between them is going to go up by 4. So it actually takes 4 times more energy to smash those nuclei into each other. And so you need that much more heat. They have to be traveling that much faster. And so the heat in the middle of the star isn't enough, because it's just as hot as it was when it was fusing the hydrogen into helium. And eventually it reaches a point where this helium core is large enough that it breaks a barrier where nothing in the center of the star is hot. There's no area in the center of the star that's hot enough to heat helium. There's no area outside of it that's hot enough to heat hydrogen. So there's no fusion happening at all, because the temperature just isn't right in any one place. And so because there's no fusion happening, there's no more reaction happening, this is actually just gas and starts to collapse again. And so the thing shrinks and starts to fall in on itself until it actually gets hot enough. These are all going to be approximate drawings, so bear with me. But until it actually gets hot enough to fuse helium, and it gets hot enough to actually overcome this force, and that's what's called a red giant. Because once that starts happening, the heat is enough that it causes the hydrogen to expand back into what we know as the red giant stage of the stellar evolutionary process. So from here, this next process, I'm only going to highlight 2. There are a lot more nuclear processes that happen in stars. I'm just going to talk about these 2 because I think they're the most important. But basically what happens is you start fusing 4/2 helium with the other 4/2 helium that's around it in the middle of this now much hotter star to form 8/4 beryllium and some other stuff. Now 8/4 beryllium is extremely unstable. Like, it doesn't want to stick around. It wants to split up pretty darn bad. It has literally like 1/100 of a second in which it has to, by chance, hit another 4/2 helium in order to actually remain stable. So if it just so happens to form, then just so happens to hit another alpha particle before it decays, it'll form a familiar 12/6 carbon in an excited state. So once you form 12 over 6 carbon, you're a lot, you basically become a balloon, because there's only a 4 in 10,000 chance of that happening to any particular helium atom that starts to undergo that process. And that's why stars live for so long, is because there are so many instances where a particle will just not reach the end of this process and decay again, and then it has to wait another million years in order to have another shot making over 12 over 6 carbon. So once it becomes 12 over 6 carbon, again you face the probability of it not releasing its excited state, because 12 over 6 carbon actually wants to turn back into 3 alpha particles again. But if it can then release a gamma ray in that short amount of time in which it has before it's going to break up due to beta decay or something like that, then you form a regular 12 over 6 carbon plus a gamma ray. And then it's reached the end. So there's a lot of probability that goes into these processes and make it a lot slower of an evolutionary process. Alright. So once that happens, things get pretty simple. I'm not going to go over all the processes that happen towards the end of the star's life. But basically, like, you end up with another ring in here where carbon is being fused together. The helium is just sitting around not being fused because it's not hot enough out there anymore. And the hydrogen is also sitting out on the surface. And what'll end up happening is that the carbon will fuse with more alpha particles, which are just sitting around in the star, and fuse into oxygen. So you're going to go from here to 16 over 8 oxygen to 20 over 10 neon. Wow, I cannot write letters. I'm very sorry. But it's just going to keep going until it reaches 56 over 28 nickel. I don't think you guys need the rest of this board. Now, by the time it reaches here, that point where it's actually trying to fuse the 56 over 28 nickel, this star looks more like an onion. So there's layers and layers and layers and layers and layers and layers and layers of different elements, spread outside of the center because they're too cold to fuse and they're too light to sink to a point where they can be hot enough to fuse. So you reach 56 over 28 nickel. And one of the processes that we went over before it becomes relevant, so you remember beta decay, if something is too neutron rich, it'll actually have one of its neutrons turn into a beta particle, and it'll have one of its neutrons turn into a proton and electrons, some other things. So this 56 over 28 nickel is actually way too neutron rich. So one of its neutrons is actually going to beta decay. One of its protons, is actually going to beta decay into 56 over 27 cobalt. 56, 27 cobalt, which then turns into 56 over 26 iron. Now, if you've studied stars at all, you know that iron is the kill switch on a star. So as soon as it starts producing iron, the thing starts to die, because first off, it's absorbing a lot of heat. There's a lot of energy that has to go into actually smashing these larger particles together. Just think about how many protons you have. Now, when you get up to like neon, it's like 10 protons, about 100 times more force that it takes to fuse those cores together than it did back when you were just doing hydrogen. And you also run into the problem that on the binding energy curve of all the elements in the universe, you actually can reach a peak at iron. So this graph right here is pretty important, because you see on the bottom of this graph the number of nucleons in a nucleus, the number of protons in a nucleus, basically all the elements arranged by atomic number, and how much binding energy it takes to keep their nuclei together. So what's interesting about this graph is that it starts at the bottom with 0 with hydrogen because there's only one proton. You don't need to stick anything together with it. And it actually goes up and then down again. So it takes more energy to make carbon than it does to make the stuff to the left, or to make iron than the stuff to the left of iron. And it takes more energy to make iron than the stuff to the right of iron too. And so you can't make anything more out of it because there's no such thing as a thermodynamically favorable process that goes past iron. And so the next stage of the process just won't happen. There's no next stage. You can't add an alpha particle to iron to make anything larger because you're just not going to get any energy out of it. And so the energy that's coming out of this star, in order to keep it stable because of the reactions that are happening, stops because there's nothing left. And so all of these layers on the outside of the star crunch into themselves and they form what we call supernova. So they smash in on each other. Think of a star that's 100 million times the radius of our sun, collapsing in a quarter of a second, all the way from its surface to whatever remains of it at its core. It creates a process so strong that you literally have protons and electrons that get smashed together into neutrons on a subatomic level. And that's what a neutron star is that all these protons and electrons in the elements in the core of this star are being just smashed together so ridiculously tightly that not only do they turn into different atomic particles, but they're put into a density that's so dense that like a spoonful of material from a neutron star is heavier than a mountain. So like it's just this ridiculous process, and the rest of the material rebounds out into space and becomes
Hey Marshall,
like a cloud.
we gotta wrap it up.
Yeah, I'll finish it up. So, yeah, that's how you use the physics that you learned in this class and nuclear physics to explain astronomy. Thank you.